What if we could hear the universe's oldest secrets, whispered on gravitational waves? Not the violent shouts of colliding black holes, but a deep, persistent hum that has pervaded the cosmos for billions of years. Or what if we could find the essential building blocks for life, the very chemical ingredients that make you and me possible, hidden in the ocean of a distant icy moon orbiting Saturn? What if we could take actual photographs of atoms as they perform their quantum dance, capturing the fleeting ghostly interactions that underpin all of reality? Or even measure particles without them ever having to meet, harnessing the strangest of all quantum phenomena. We live in an age where these aren't just thought experiments, they are today's headlines. Welcome back, fellow cosmic explorers, to another journey into the known and the unknown. We're venturing to the very frontiers of human knowledge, where the line between science fiction and scientific fact is blurring with every new discovery. In this voyage, we're not just taking small steps, we're witnessing giant leaps for all humankind. We're going to explore 5 of the most mind-blowing recent breakthroughs in cosmology and quantum physics, discoveries that are actively rewriting our textbooks, challenging our deepest assumptions about the universe, and paving the way for a future we can only begin to imagine. These are not just incremental updates, they are paradigm shifts. First, we'll tune our cosmic radio to listen to a gravitational hum that echoes the waltz of supermassive black holes across the universe. Then, we'll travel back in time with the James Webb Space Telescope to witness the very dawn of creation, where we found galaxies that, according to our old ideas, simply shouldn't exist. From there, we'll dive into the subsurface ocean of an icy moon, Enceladus, to find a key ingredient for life itself. We'll then zoom into the impossibly small to see the first ever snapshots of individual atoms interacting in free space. And finally, we'll unravel the spooky logic of quantum entanglement, a phenomenon so bizarre Einstein himself couldn't accept it. These discoveries matter profoundly. They are more than just answers to old questions. They are keys that unlock entirely new realms of inquiry. They push the boundaries of what we thought was possible, revealing a universe that is far more complex, more surprising, and more magnificent than we ever dared to dream. They hint at a future filled with even more astonishing revelations and technologies we can't yet conceive. So buckle up. Our journey into the heart of space, time, and the quantum realm begins now. The cosmos is calling, and we must go. Imagine the universe as an immense ocean. For most of human history, we've only been able to study it by looking at the light glinting off its surface. But what if we could feel the currents themselves, sensing the deep, powerful movements driven by the most massive objects? This is the promise of gravitational waves, ripples in the very fabric of space-time. Observatories like LIGO and Virgo have detected the violent, high-frequency shouts of gravitational waves. These are the cataclysmic signatures of stellar-mass black holes and neutron stars spiraling into each other. But what about the low, persistent background music of the cosmos? Physicists have been searching for a persistent, stochastic gravitational wave background. Finding this hum would be like finally being able to hear the ambient sound of the cosmic city. And now, after decades of patient listening, we've heard it. A consortium of scientists called Nanograv has announced the first compelling evidence for this cosmic hum. You can't build a detector on Earth big enough, so you build one that is the size of our galaxy. They use some of the most reliable, most precise clocks in the entire universe, pulsars. If a gravitational wave passes through our galaxy, it should subtly alter the very fabric of space between us and the pulsar. After a decade and a half of meticulous data collection and analysis, Nanograv found that exact pattern. The prime suspects are the true titans of the cosmos, supermassive black holes. When two galaxies merge, their central supermassive black holes will eventually find each other and begin a long, slow gravitational dance. The universe is filled with galaxies, and so it must be filled with these spiraling pairs of supermassive black holes. This discovery gives us a completely new way to study how galaxies grow and evolve. The beauty of this new observational window is that it could reveal physics that we've only ever dreamed of. Detecting this signal would be the holy grail of observational cosmology. We have opened a new sense with which to perceive the universe. What we've found so far is amazing, but the true excitement lies in what we might hear next. There is no more profound human question than, where did we come from? On a cosmic scale, that question becomes, where did everything come from? Where did the stars, the galaxies, and the great cosmic structures we see today originate? A grand narrative that begins with a hot, dense Big Bang and unfolds over 13.8 billion years. When the very first stars and galaxies flickered into existence, to see into this ancient past, you need more than a telescope. And that's precisely what the James Webb Space Telescope is. Because light travels at a finite speed, about 300,000 kilometers per second, looking out into space is the same as looking back in time, with a massive gold-coated mirror kept at incredibly cold temperatures. It is a machine built for one primary purpose: to capture the faint, red-shifted light from the first galaxies to ever form. And in its first year of operation, JWST has succeeded beyond our wildest dreams. It has peered deeper into the cosmic darkness than ever before, pushing back the frontier of observation to just a few 100 million years after the Big Bang. It is the cosmic equivalent of finding the first ever fossilized cells from the dawn of life on Earth. We are, for the first time, witnessing the lighting of the cosmic fires, the assembly of the first island universes. And what we are finding there is not what we expected. Makes a clear prediction about what the early universe should look like. It tells a story of gradual, hierarchical growth. Small, wispy clouds of gas and dark matter should slowly coalesce, forming the first small, dim proto-galaxies. Over hundreds of millions of years, these small building blocks would then merge and grow, eventually forming the large, majestic spiral and elliptical galaxies we see in the universe today. It's a bottom-up process. Small things form first, and big things form later. JWST pointed its golden eye towards the most distant and therefore youngest regions of the cosmos and found something bewildering. It found galaxies that were far too big, far too bright, and far too mature to exist so early in the universe's history. These galaxies, seen as they were just 500 to 700 million years after the Big Bang, appear to contain as many stars as our own Milky Way does today. According to our models, there simply hasn't been enough time for them to grow that large, where you only planted a seed yesterday. These objects challenge the very foundations of our understanding of galaxy formation. Some of these galaxies appear not only to be massive but also to have complex structures like galactic disks, which were thought to take billions of years to form and stabilize. They seem to have formed stars at a furious rate, far more efficiently than our theories would allow. It's as if the universe had a fast-track mode for building galaxies that we knew nothing about. Does star formation happen much more explosively and efficiently in the pristine gas of the early universe? Or could the universe itself have been expanding differently, or have had different initial conditions than we currently assume? These are the questions that are keeping astrophysicists up at night, scrambling to make sense of these beautiful, defiant, and impossible galaxies. Are we interpreting the data correctly? In the case of these surprisingly bright early galaxies, one major assumption is that all the light we're seeing is coming from stars. We measure the brightness of a distant galaxy, and from that, we infer its stellar mass, the total mass of all its stars. What if there's a brilliant masquerader hiding in plain sight, making these galaxies appear much more massive than they truly are? Enter the active galactic nucleus, or AGN. This is the intensely luminous, compact region at the center of a galaxy, powered by gas and dust accreting onto its central supermassive black hole, causing it to shine with an intensity that can outshine all the billions of stars in its host galaxy combined. If some of these early bright objects are not just galaxies full of stars, but are in fact hosting powerful, rapidly growing supermassive black holes, it could help resolve some of the tension. JWST has in fact found evidence for AGN in some of these very early galaxies. This is, in itself, another puzzle. How did supermassive black holes grow so large so quickly? The intense light from an AGN could be contaminating our measurements of the galaxy's starlight, tricking us into thinking the galaxy has a much larger stellar mass than it actually does. The galaxy might not be impossibly massive after all, it might just have an impossibly bright quasar at its heart. Instead of asking how did so many stars form so quickly, we might instead be asking how did so many supermassive black holes form and grow so quickly. It suggests that the growth of the first black holes out there, in the cold, dark expanse between the planets, orbits a tiny, icy moon, Enceladus. For centuries it was thought to be geologically dead, encased in ice. But Cassini revealed a hidden liquid ocean beneath its icy crust, venting its contents into space. Cassini tasted those plumes, sending back a chemical postcard. It found salt, carbon dioxide, methane, ammonia, and complex organic molecules, the very kinds of ingredients that on our own world came together to form life. But one crucial ingredient remained missing: phosphorus. Without it, DNA itself could not exist. Phosphorus is critical. It's the P in ATP, the energy currency for all cells, and forms the backbone of DNA and RNA. When we look for life, we look for the Knops elements. So where was the phosphorus on Enceladus? The breakthrough came from a deeper look at old data. The unmistakable chemical fingerprint of sodium phosphates was found. Phosphorus wasn't just present, it was abundant, possibly hundreds of times higher than in Earth's oceans. The final crucial ingredient for life was confirmed. Enceladus is arguably the most promising place in our solar system to search for extraterrestrial life. The habitability checklist is now complete. A long-lived liquid water ocean, a source of energy, and all the necessary Knops elements. If you have all the right ingredients, does life inevitably arise? Enceladus offers us a tantalizing opportunity to find the answer. It's a call to action. We must go back with new explorers, armed with specialized instruments, to search for biomarkers. Future missions are being designed to do just that. The ultimate goal would be to land on the surface and analyze a sample directly. The discovery of phosphorus has reshaped planetary exploration. We possess both the knowledge of where to look and the technology to go there. The potential reward is the greatest in all of science, the discovery that we are not alone in the universe. For millennia, we have looked up at the stars, marveling at the grand cosmic ballet. But there is another universe, equally vast and mysterious, hidden within every speck of dust, the quantum realm. Here, particles exist in a haze of probability, their properties undefined until the moment of observation. Seeing them as individuals, as distinct entities in their natural unbound state, remained a dream. Atoms are unimaginably small, and they move with blistering speed. To see one, you have to cool it down to near absolute zero, slowing its frantic dance. But what if you could catch them, floating freely in the vacuum of space? It's about witnessing the fundamental building blocks of matter in their purest form. Recently, a team at MIT achieved this seemingly impossible feat. They didn't just glimpse an atom, they took its picture. This breakthrough is a new window into the quantum world. The universe at the smallest scales will never look the same again. The scientists at MIT developed a technique of stunning ingenuity. It begins with a cloud of ytterbium atoms, cooled to just above absolute zero. Instead, the researchers use a precisely tuned laser that resonates perfectly with the electrons in the ytterbium atoms, causing them to fluoresce. A sophisticated high-resolution microscope gathers the scattered photons, pinpointing the exact location of each individual atom. The team developed a way to do this repeatedly and non-destructively, creating a stop-motion movie of atomic behavior. For a century, quantum mechanics has been the bedrock of modern physics. Seeing individual atoms interact freely provides a new, more direct test of the theory. The results are a stunning confirmation of what the theory has been telling us all along. We are watching it happen, atom by atom. We have a new tool with which to explore the very foundations of existence. It is the key to unlocking a new technological revolution, the dawn of true quantum engineering. This technique provides the visual feedback necessary to manipulate matter at its most fundamental level. This technology could also revolutionize our understanding of chemistry and material science. This breakthrough is a foundational tool, much like the invention of the telescope or the microscope. We have taken a photograph of the building blocks of reality. Now the real work begins, using that knowledge to build a new future, one atom at a time. There is a mystery at the heart of the quantum world so strange, so contrary to our everyday intuition, that Albert Einstein famously called it spooky action at a distance. This phenomenon is known as quantum entanglement. Imagine you have two coins, but these are special quantum coins. You flip them and they are sent to opposite ends of the universe. The moment you look at one and see that it's heads, you know instantaneously that the other coin, light years away, must be tails. It's as if they are connected by an invisible thread, their fates linked no matter how far apart they are. Before you looked, each coin was in a state of superposition, a mix of both heads and tails. But the act of measuring one instantly collapsed the state of both, forcing the distant coin into a definite outcome. This connection appears to be faster than light, a violation of what Einstein held sacred as the ultimate speed limit of the cosmos. This apparent paradox has puzzled physicists for decades. How can two particles separated by vast distances coordinate their actions in no time at all? This spooky connection is not just a theoretical curiosity. It is a real measurable property of our universe. Experiments have repeatedly confirmed that entanglement is genuine. closing one loophole after another that might have allowed for a more classical, common-sense explanation. There are no hidden signals passing between the particles. It's as if, in the quantum realm, the concept of distance itself becomes secondary. For entangled particles, the universe is a smaller place. Understanding and harnessing this bizarre property is one of the paramount goals of 21st century physics. If we could control this invisible, instantaneous connection, what could we achieve? It promises to be the engine behind a new generation of technologies, unhackable communication networks, ultra-precise sensors, and computers with unimaginable power. We must find new ways to use this quantum link to make it do work for us, to turn a cosmic mystery into a powerful tool for discovery and innovation. Traditionally, to learn something about a particle, you have to interact with it directly, bounce another particle off of it. It inevitably disturbs the very system you are trying to observe. In the delicate quantum world, this disturbance can be catastrophic, destroying the fragile quantum state you wish to study. The very act of checking pops the bubble. This is the fundamental challenge of quantum measurement. What if you could measure a particle without ever touching it? This is the promise of a remarkable new technique demonstrated by physicists at the University of Geneva. They have shown that it's possible to use the spooky action of entanglement to perform a measurement by proxy. You start with two entangled particles, let's call them particle A and particle B. Their fates are linked. You keep particle A safe in your lab, while particle B is sent out to interact with the object you want to measure, let's call it the target. When particle B interacts with the target, its properties are subtly changed. It might get a tiny nudge, or its wave-like properties might be shifted slightly. Because particle B is entangled with particle A, any change to B is instantaneously mirrored in the state of A, even though A is sitting safely back in your laboratory, having never come close to the target. The invisible thread of entanglement transmits the information about the interaction from particle B to particle A. By then carefully measuring both particle A and particle B and, crucially, the correlation between them, the scientists can reconstruct what happened to particle B during its interaction with the target. They are essentially measuring the disturbance itself. Because they are looking at the relationship between the two particles, information that would have been lost in the noise of a conventional measurement. To see the unseeable and measure the unmeasurable, all without popping the bubble. The experiment conducted at the University of Geneva was a beautiful proof of this principle. The scientists used entangled photons, particles of light. One photon from an entangled pair was sent on a path where it interacted with a delicate object, in this case a tiny vibrating crystal. A traditional measurement would have struggled to even detect such a minuscule effect, as the noise from the measurement process itself would have overwhelmed the signal. The second photon from the pair, however, was kept pristine, traveling a separate path and never interacting with the crystal. When both photons were finally detected, the physicists looked at the correlations between their arrival times and properties. Because of entanglement, the subtle changes imprinted on the first photon by the vibrating crystal were also reflected in the correlations between it and its untouched twin. The information was there, encoded not in one photon alone, but in the spooky link that connected them. This technique of entanglement-assisted measurement allowed them to detect the crystal's vibration with a sensitivity that would have been impossible otherwise. They used the ghost of a touch to measure a real object. This demonstration moves entanglement from the realm of mind-bending thought experiments. It proves that we can leverage the strangest feature of quantum mechanics to overcome one of its greatest challenges, the observer effect. This method could be used to image fragile biological samples like proteins or viruses, without damaging them with harsh X-rays or electron beams. We could see the inner workings of living cells in their natural state. It could be used to create sensors capable of detecting the faintest magnetic fields or the most subtle gravitational shifts, but to use its own bizarre rules to our advantage, turning its spookiness into a source of strength. This breakthrough is a cornerstone for the emerging age of quantum information science. This new field treats quantum phenomena like entanglement and superposition. Information in this view is a physical quantity, and the rules of quantum mechanics provide a new and powerful instruction set for how to process, secure, and transmit it. Entanglement-assisted measurement is a prime example of this new paradigm in action. Think about secure communications. Quantum communication networks, which are already being built, use entanglement to guarantee security. If an eavesdropper tries to intercept the message, breaking the entanglement and immediately revealing the presence of the spy, this is not just difficult to hack, it's impossible to hack. guaranteed by the laws of physics. The work at Geneva refines the tools we need to build and operate these future networks. Beyond communication, this technology will be vital for quantum computing. A quantum computer's power comes from the delicate, entangled states of its many qubits. To build a useful, large-scale quantum computer, we need to be able to measure and control these states with exquisite precision, without destroying the very computation we're trying to perform. Entanglement-assisted measurement provides a pathway to gentle diagnostics, allowing us to check on the health of a quantum computation without derailing it, a crucial step toward fault-tolerant quantum machines. Just as the discovery of the electron a century ago ushered in the electronic age, our growing mastery over entanglement is heralding the quantum age. From metrology and sensing to computing and communication, we are learning to speak the universe's native quantum language, into the engine of a technological revolution that promises to reshape our world in ways we are only just beginning to imagine. The future is quantum. We've journeyed from the edge of the cosmos to the heart of the atom. We've listened to the gravitational hum of colliding supermassive black holes, a sound that has been traveling across the universe for billions of years. We've peered back through cosmic time with the James Webb Space Telescope to witness the unexpected, brilliant dawn of the first galaxies, challenging our very story of cosmic origins. We have found the chemical signature of life's building blocks in the plumes of an icy moon, transforming a distant world into a beacon of hope in our search for neighbors. The universe, it seems, is far more creative and far more surprising than we ever dared to dream. And as we look deeper into the very fabric of reality itself, the wonders only multiply. We've captured the first photographs of individual atoms floating freely, turning the abstract rules